given a fixed number called a. It needs to be positive, so a greater than 0. And that number a is called the base. An exponential function is a function whose formula is of this format: f of x equals a to the x power. So for example, f of x equals 2 to the x. That's an example of an exponential function. This is what would model the number of bacteria you have after x hours if bacteria double every hour. For example, g of x equals 3 to the x is another example of an exponential function. H of x equals e to the x is another example of an exponential function. Don't let the e throw you off. E is just a number. It's about 2.7. So 2 to the x, 3 to the x, e to the x, these should all treat them all just the same. There's no need to treat the e as if it's something real different or anything like that. K of x equals 5.7 to the x power. This is an example of an exponential function. In fact, this models the number of people who are newly getting infected with COVID. Where did 5.7 come from? This base number here, 5.7, is actually known as R naught in the infectious disease research. So if you look up things, you should look up some things online, Google for this R naught, and that number, we want that number to be small to make sure that that not as many people are newly getting infected. But at least in a quick lookup, I found the number 5.7. So applications of exponential functions, based on what you see here, when the base is a big, relatively big number like 2, 3, e, 5.7, so on, this ends up modeling population of things, typically of living organisms such as humans or bunnies or disease, viruses, right? Or continuously compounded interest. So these are all examples of things that grow. Here's the thing. In an exponential function, that base here, a, is required to be bigger than 0, and there's a very different kind of shape that you get, in a sense, when a is positive. So when a is, okay, a has to be positive, but the shape looks different when a has to be bigger than 1 versus when a is between 0 and 1. So here's the picture of a bigger than 1. The graph ends up looking like this, and grows up like that and shoots up rather quickly. And then over here, this picture is what happens when the base is between 0 and 1. We actually saw an example of this kind of thing yesterday, but to really categorize, now look, as you move along the x-axis, as you look at x big, x, 5, 6, 7, 8, 9, 10, so on, and x usually represents time, then the number of the thingies that you have is shrinking rather a lot. So this case here, where the base is bigger than 1, models growth, like a pandemic, but the case when the base is between 0 and 1 also models something, and that's called exponential decay. There are real examples of exponential decay. One of them is radiocarbon dating. So a function like where the base is, 0.000237. Okay, so 0.000237 raised to the x, so that base is smaller than 1. This base is between 0 and 1. This models, for instance, how much carbon is in a fossil based on a fossil that is x years old. Okay, so as x increases, the amount of radiocarbon that you find in that fossil is getting smaller and smaller, but because we know what the curve should do, we can actually predict the age of a fossil based on this. Okay, another example is half-life. So a function like, again, the base has to be between 0 and 1. So like, how about the base being 0.852? So that number as the base raised to the x power, this models, how much of a certain medicine is in someone's body x hours after they take the medicine. And this is very important. If you have to administer medicine to somebody, this is something, even if you're not going to be a doctor or a nurse, even if you just have a life partner that you need to sometimes administer medicine to, you should know something about what half-life, this is called half-life very often, of what's going on with medicine. You don't want to accidentally cause somebody to overdose, right? So computing this is important for being able to administer medicines to somebody without overdosing. Okay, so let's review some properties we've seen for exponential functions. So if you have the base is a fixed number bigger than 0, then the exponential function f of x equals that fixed number raised to the x. So that fixed number could have been 2, so like 2 to the x, or 3 to the x, or e to the x. A function of that format will always have the following properties. The domain is all reals. The range is all reals bigger than 0, so you see that 0 is excluded with this parenthesis here. The horizontal asymptote is the x-axis. Another way to write that is to write y is equal to 0. The y-intercept is 1, and there are no x-intercepts. Okay, when writing the horizontal asymptote, be sure to write y equals 0, not just 0 alone.